Who's Raju Venugopalan from Brookhaven, Stony Brook, and the Higgs Center. Please.
Thank you very much. Yeah, it's a great pleasure to be here in Cambridge at the Newton Institute, and I thank the organizers, Frank, Chris, and Andy O'Bannon, who lives on Long Island alongside me, for inviting me to come here and give this talk. And when I discussed this with Andy, it wasn't clear that, you know, what you're talking about and thinking about has anything to do with what I'm talking about and thinking about. And so that's a question mark here. Namely, what does this program on boundaries and defects and impurities on QFTs have to do with QCD, the real world, where we're describing a quantum field theory that explains how subatomic particles collide. So what I'm going to be talking about are actually objects which are hotspots inside these hadrons or nuclei at distances of 10 to the minus 19 kilometers. So that's a tenth of a Fermi. And I hope I'll convince you that there's some deeper connections here that remain to be explored. And the value in that is you'll be doing something related to something absolutely physical and relevant for the real world with tremendous consequences. So one consequence of this is, stuck. Is this. So this is a hadron-hadron collision at the LHC. And so, you know, they have these beautiful sort of timelines of when it was actually recorded and so on. So this is a proton-proton collision at LHC at very high energies. What you see is hundreds of particles coming out in this collision of these two subatomic objects. And the question is, you know, how do we understand this? Can we explain this in some regime of systematics in some convincing way? And so the problem in QCD or in quantum field theory is multi-particle production in high energy QCD. So Andy's here right on cue. So how do we think about this problem? And so this is actually a very old problem. What you could think about it in terms of, you know, how do you produce 2 to n particles? What is the amplitude for 2 to n scattering in QCD? And so if you think about this is an enormously difficult problem. You have n factorial diagrams, Feynman diagrams that you have to deal with. And so the problem is exponential in complexity, and even quantum computers will be challenged to actually compute this from first principles. However, there's a very beautiful limit, which holds the name Reg next to it, is that in a certain kinematics, you can actually make an attempt to actually compute this in first principles.
I found this on the web.
No, you didn't. So the problem is, you know, two very energetic gluons, say, coming from one, say, each from a hadron, right? That's the event I showed you. And then they kind of bifurcate and produce lots of these particles. And so the kinematics that I'm talking about, multi-radial kinematics, oops, this is gone. It's not working anymore. So multi-radial kinematics is where the particles, as you go down this ladder, are ordered in a variable called rapidity. So you can think of it as a velocity. And so as you go down the ladder, the particles, the longitudinal momentum of these particles gets softer and softer. So they're slower and slower. And that's what ordering and rapidity, that's these y's shown here. But they are, all these particles have the same, approximately the same transverse momentum. And it's large, okay? So it's much larger than the intrinsic scale of the theory, which is lambda QCD. And that's very important because you can compute in weak coupling. So we know asymptotic freedom tells you the coupling was run as a function of the larger scale. And if that scale is large, then you can actually try and compute this. But the partons that are produced are in Feynman's language, they're wee in their longitudinal momentum. So they're slow in that direction, but hard in transverse momentum. So this is the recoupling multi-radial regime in QCD. So these authors here by this acronym, Belitsky, Fadin, Kuraev, and Lepadov, already 50 years ago, showed how you could actually compute such a diagram, in particular kinematics. And what they showed is that if you take all your n factorial diagrams and you organize this in this multi-radic kinematics, a ladder structure emerges from this, okay? As shown here, where you can, because if you think about arbitrary refinement diagrams, it's not obvious at all that you get a ladder structure, but they show there's an emergent ladder structure with effective propagators which go down the ladder and vertices that produce these gluons, partons in the final states. And the labels there are their spin and color labels, and the momenta are shown as K and L as you go down the ladder. And so it turns out that this ladder is also described by Hamiltonian, so it has a renormalization group picture that emerges. And the BFKL Hamiltonian is enormously rich, so it has a very rich mathematical structure. I won't go into that here, but rest assured it's been well studied and plumbed in literature and has led to an enormous outpouring of work. Interestingly, and I won't talk about this later here, but if you're interested, there's an identical structure for multi-graviton production in gravity. So there's a BFKL equation in gravity. And if you're interested, you can look at my recent review with my postdoc, Himanshu Raj, from slightly earlier this year. So let me, since this is such an amazing thing, if you think about it, this organization of n factorial diagrams into such a ladder structure, let me just go through a little bit the elements of the structure to give you a sense of how this arises. So the building blocks, as you look at each rung of the ladder, so imagine you're just standing at, you're looking at one rung of this ladder, and you're saying, what is that blob that's there, and what's the dark line that's going down, right? So if you just concentrate on one such rung, and then you say, okay, let me think about a 2-to-2 subladder, and let me think of adding all the 2 to 3, the 5-point amplitudes I can construct. So you add them all up. And it turns out, again, this multi-radial kinematics, where this particle that's emitted is slower than the other particles, you can sum up all of these diagrams using the Jacobi identity and write this as one effective vertex, which has, again, this kind of ladder structure, where this effective vertex is not a local object, it's a non-local object. It's a function of the momenta being exchanged, and has a structure as shown here. And this is sometimes called the Lepadov vertex. Now this object is manifestly gauge covariant, and it has very nice properties. Now, so that was the object that is the vertex for the emission of this 5-point amplitude. Now, this object that was being exchanged down the T channel, that's sometimes called T channel in the scattering. Yeah, this is very faint. It's not really working.
You want to stick on the board?
Actually, stick is even better. Oh, thank you so much. This is great. So, thank you. So this object that's being exchanged is sometimes called a radioized gluon. And what the radioized gluon is an object that's summing up all of these loop graphs, which are computed in multi-radial kinematics. Okay, so you have to impose multi-radial kinematics, but it computes all loop graphs to all orders. And what that does in multi-radial kinematics is replace the bare propagator, which is 1 over this momentum transfer, this is a Mandelstam variable t, by this exponentiated form here, where again, this is the difference of these rapidities or velocities that I mentioned, logs of the velocities. And this alpha is sometimes called a radial trajectory. So this is the radial trajectory. You can compute this in perturbation theory, and it has this kind of structure here. It has a logarithmic divergence. But then when you compute actual physical quantities, that infrared divergence cancels, and you get something finite. So essentially, there are two objects. The Lepadov vertex sums of all these two to three objects into one effective vertex, which is non-local but gauge covariant. And the radioized gluon sums up all of these horizontal loop contributions into this very elegant form here, characterized by the radio trajectory. So now you can ask yourself, okay, what happens if I were to try and compute the 6-point amplitude? Okay, so now imagine I'm emitting another additionally soft gluon, and even with that restriction that it'd be soft, I have about 40-odd Feynman graphs to compute. And you can imagine the number just explodes as you go to higher point amplitudes. So what do? And so the brilliance of Lipatov and collaborators was to realize that you can use dispersive methods. So this goes back to S-matrix theory already from the 60s, but applied to QCD. So you can use dispersive techniques to actually make progress. So the first thing you can do is you can just look at the 2 to 3 amplitude. So the 2 to 3 amplitude that I showed you previously here, so can be written as an object whose building block is just the 2 to 2 Born amplitude. So you just have 2 guys coming in, 2 guys coming out with T-shell exchange. And so these are the color labels of the incoming and outgoing guys, and these are the momentum labels of the 2 to 2 process. And you can write that. You can do a Feynman diagram computation, and you see that it's just the 3-gluon vertex with the momentum and color labels, the center of mass energy squared, Mandelstam variable T, and another such object here. It's very simple, right? It turns out that that's all you need to reconstruct the 2 to n amplitude. Okay? And so the way you see it is that you say, okay, now let me do this 2 to 3 amplitude. Okay, so this is also something you can compute, using Feynman diagrams exactly. But let's do it with this dispersive approach. So what you do is you first, cut this 2 to 3 amplitude here. Okay, and you ask, what's the residue of the pole of this cut? And that can be written in terms of just this 2 to 2 object here, which is this guy here. Then the energy factor times just the 3-gluon vertex here, right, of this guy. So now this residue, by the way, contains a pole, right, which is this exchange of K1 in here. So there's a hidden pole in here. And you can do the same thing by cutting the one above. So you can cut that one instead of this one. And the same thing holds in reverse. And you can then identify the common factors in these 2 residues and reconstruct the entire 2 to 3 amplitude. Okay. And when you do that, you get this result. So you have this common poles here, K1 squared, K2 squared. You had, again, these 3-gluon vertices from both ends, right? There's a structure constant, and then you see that the Lipatov vertex comes in multiplied by a polarization vector. Okay? So these are on-shell amplitudes, so you have to project this onto physical polarizations. And so you see that in this way, you recover very simply, without doing all the Feynman diagrams for the 2 to 3, you actually recover this Lipatov vertex. And this process can be iterated to all orders to construct the BFK ladder for 2 to n. And that's the structure that you get. So this is a 2 to n ladder. So you have these regularized gluons, and this is containing all loops to leading log accuracy, as it's often called. And then you have these effective vertices and propagators going down. Now, if you want to construct the total cross-section by the optical theorem, you know that that's related to the imaginary part of this 2 to n guy, right? Or this 2 to 2 amplitude, sorry. And so you can actually compute this 2 to n guy, compute this, take their product, sum over all intermediate states, and that'll give you the full 2 to n, the imaginary part of the 2 to 2 amplitude. Now, this object is still very complicated because remember, I have all these Lipatov vertices and these color factors and momentum factors being iterated down this ladder. It's still a very complicated object, right? And then I take the modulus squared, it's even more complicated. Now, it turns out that if I normalize this by the Born amplitude and take the Mellon, look at it in Mellon space, so I do the Mellon transform of this, this object can be written in terms of this very simple function of these variables here, k, which is a dummy variable, and q, which is the momentum transfer. And it turns out that this object can be described by a very simple integral equation, which is the BFKL equation in momentum space. So this enormously complicated 2 to n amplitude, right, with n factorial Feynman diagrams, has as a result this very simple integral equation that reconstructs the cross-section for this process. And this object here is just the scalar product of the Lipado vertex, so it has this nice structure. So you see, it's really very visual. You take the product of these two Lipado vertices, that gives you this object here, and then you get the radial trajectories coming from all the loops that are being summed here, and in this, on both in the amplitude and the complex conjugate amplitude, that's what these refer to, and you get this very, very elegant structure of the total cross-section. Now, this integral equation can be solved very simply, and you can do that in terms of the Fourier conjugates of these momenta. So one is in terms of the conformal spin, that's nu, and the azimuthal variable n, the angle between these two momenta. And you see that as a function of the conformal spin, you can take the saddle point with the corresponding path integral, and that's dominated by a particular value that's given here. And then if you do the inverse Mellin transform, that tells you the cross-section, and it tells you how QCD cross-sections grow as a function of energy. So from 2 to n, you can actually reconstruct this. Now this is very rapid growth of the cross-section, and it certainly can't be true asymptotically, because there's a theorem due to Froissart and later elaborated on by Martin, which says that in any gauge theory with a mass gap, the cross-section cannot grow faster than the log squared of the energy asymptotically. So it's only an asymptotic bound, so there's nothing at finite energies, but eventually you're going to have a problem with that. But, and people have actually done systematically in this BFKL framework, gone to higher orders, gone to 2 loops and further to some extent. And they find that this growth is dampened a little bit. So it's instead of 0.5, it's 0.3 for reasonable values of the coupling, but it's still a much faster growth. But this is, however, what you see in data, okay? So these are parton distributions inside the proton. So that's the number of gluons inside the proton, the number of C quarks inside the proton, at some fixed resolution, as a function of this rapidity variable, which is sometimes called Bjorkian X. So you're going to higher and higher energies, you're going this way. Okay? So with energy, you go this way, and you see the number of these partons grows, and this is a logarithmic scale, so it's growing extremely rapidly, right? It's as an exponential order to the rapidity, or as a power law in this X value here. And so a nice visual way to think about this is that you think about a hadron, and it's as you boost the hadron, it Bremsstrahlens more and more gluons. And then if you measure these at some fixed resolution scale, that's the number of gluons that you see in your experiment. And that's physics is described very well by BFKL. However, as I mentioned, the growth is very, very rapid. And so the question is, what happens? So if you think about, 2 hadrons scattering, and you see all this tremendous radiation that's going on, and that radiation is growing as you increase the energy, is that hadron going to blow apart, right? I mean, is it a runaway popcorn machine? That strange burst is lit as you produce more and more of these gluons inside. In other words, what happens to the phase space density of these gluons inside the hadron? Now, it turns out that there is a problem that one sees with this BFKL construction that I mentioned, which is that the wanted operator per expansion that we believe should be true in quantum field theories breaks down in a particular way, in a particular sense. And so what you find is that if you remember, I said early in my talk that the amplitude, when you construct the amplitude, you assume that all the produced gluons are hard. They have momentum much larger than the lambda QCD scale. So you can use weak coupling to compute the 2-to-n amplitude. But they're soft in longitudinal momentum. Now, as you boost the hadron even more and more, as you access softer and softer momenta, what you find out is that this construction then goes into the infrared. Okay? So the construction, the solution doesn't satisfy the conditions of the construction, and this is kind of a problem. Okay? And that's a statement from this very nice paper by Alan Mueller, where he says that, and that is true for arbitrarily large momenta. So if I think about a scattering problem where there's a very large momentum transfer scale, q squared, where the gluons are initially peaked, it doesn't matter. There's always a rapidity value or a V parton fraction, x, below which the OPE breaks down. Now, and I'll explain that in a more qualitative way shortly. And it turns out going to higher loops doesn't actually cure this infrared diffusion problem. So what's going on? It's not that the OPE is breaking down in the sense as a fundamental feature of quantum field theory. It's just that higher twist OP corrections, which are power suppressed usually with powers of the momentum transfer in the problem, they become large. So instead of these ladder construction, where you think about these as Bremsstrahlung gluons in this ladder, you can have such higher twist operators start to become very important. Okay? And so as you go to higher and higher energy, the rapid growth in the cross-section makes these kind of viable. And what happens is a phenomenon called gluon saturation. Okay, so let me just explain what I mean by that in this nice cartoon. So imagine you have a scattering process where you have some momentum transfer resolution scale, which is a log of the momentum transfer, and then you boost the object also at the same time to higher and higher energies. So that's a log of energy, a log of the Feynman variable x. So even if you are a very large q squared, where you feel that weak coupling techniques, perturbative techniques in QCD should be applicable, as you boost, and that's this BFKL construction, the number of partons grows very rapidly, as I mentioned in that computation earlier. And at some point, the hadron becomes just overpopulated. Okay? And it doesn't matter, how high a scale that you start with, there's always a value of x, or always a value of the rapidity where you will saturate this bound. Okay? And that happens when the occupancy, phase space occupancy inside the hadron is on the order of 1 over the coupling. Now it turns out that that's also the value at which one unitarizes the cross section. So what this tells you is that if you have an object that's scattering off a high energy hadron. So imagine you're a tiny, tiny object and the hadron's being boosted towards you. The statement is no matter how tiny you are, at sufficiently high energy, you're going to interact with this as if it were molasses. Okay, so it's going to be with unit probability. And that's even, so perturbative QCD would tell you that, well, the coupling gets weaker and weaker, asymptotic freedom as you go to small and smaller resolutions. So it should really go through. But what this phenomenon is telling you is that at some point you're going to get so dense at an arbitrarily small scale that you're going to unitarize the cross-section locally. And so what you're doing is you're forming semi-classical lumps inside the hadron. Okay, so these are, so here you have this intensity quantum object, right? And you're kind of boosting at higher energies. But what happens is the phase space density becomes on the order of 1 over the coupling. Okay, and perturbation theory just breaks down. And that happens at scales which are still large, right? So they saturate. So and you can do so. So you can think about these lumps as closely packed gluons, which are described by some saturation scale x at some given impact parameter of the scattering. Okay. But because you have a weak coupling scale, you can describe this very strong field, non-protodynamics, systematically in recoupling. Okay? So that's really a very rare phenomenon that we have actually in nature, where you can really actually compute strongly correlated dynamics, okay, in a kind of Lorentzian kind of Minkowski framework, okay, systematically in recoupling. So this sort of very rich dynamics that emerges. So how do we describe, so as I said, perturbation theory breaks down. So how do we understand this? And this is where the interface to what you might be thinking about starts to emerge. Okay, you're like, why is this guy talking about amplitudes? What does this have to do with what we're interested in? So the way you can think about it, so you want to think about how you would construct such a saturated semi-classical gluonic object in quantum field theory. So one way to think about it is that now think of the scattering. So it's always useful when you think about any kind of physical process, right, in quantum field theory or quantum mechanics, to imagine an experiment. And so here you imagine there's some electron that commits, emits a virtual photon, goes into a pair of quarks with some size. And then that's probing very deep inside your hadron nucleus, you know, these over-occupied object that I mentioned, these saturated gluons. Now, if you're in the target rest frame, then what you see is the target's at rest, and then the projectile is going to be boosted towards it. Conversely, you can think in the target, in the projectile rest frame, where the projectile is at rest and the target's kind of coming at it. So then what it sees is this highly Lorentz contracted shock wave. Okay? And the scattering is then can be described as the radiation in the presence of the shock wave. Now, in that frame, so what you see is these partons are essentially moving along the light cone. And so if you think in light front, then these are kind of Galilean. So essentially they're like static sources living in the light cone. So the sources are like static sources, and then they're coupled to dynamical gauge fields, which are living in the bulk. So these sources are kind of Lorentz contracted to sheet, and then in principle you have the bulk gauge fields around it. And that's the object that scatters off your projectile. So what this tells you is that there must be a kind of Born-Oppenheimer EFT where you construct the dynamics of these guys here, right, which scatter the probe, in terms of the separation between the static sources and dynamic fields that they couple to. And you could write down the generating functional for this effective action, where you have some gauge invariant stochastic distribution of the sources. Now you have to imagine, so what do you call sources and what do you call fields, right? I mean, you have the scattering that's going on. So you say, okay, let me arbitrarily put some momentum, right? Some particle I describe as slow, as everything that's below this scale here, and that's this lambda plus, okay? And you say everything that above it is fast, right? So the stuff below is on the light cone, the stuff is off the light cone, and they're slow. Now the guys that are on the light cone are static, and you assume that it's some kind of random distribution of these guys, okay? So that's an approximation, which turns out to be valid in a particular case I'll come to. But for now, just assume you have some stochastic distribution of sources or impurities in which you describe the dynamics of these bulk fields, okay? And that's given by the full QCD path integral, which has a gauge invariant coupling, okay, to the sources. So these sources are these rows that I described here. The gauge fields are the A's that describe these objects here. Okay, and so this is the QCD path integral. I've left out the fermionic fields for now. They can also be included. But they have this gauge invariant coupling to a path-ordered exponential, right, of the of the gauge, the coupling of the gauge fields to the sources as they move along the light cone. So the sources are moving with a very large momentum P plus, and so they couple predominantly to these gauge fields X minus. Okay. So if I want to compute any arbitrary operator, so say the scattering of this object, the S matrix for this object, then the expectation of that value of the operator is evaluated with this path integral, right? And then you have a stochastic distribution of these sources with which this is weighted, okay? And that's where the glassy aspect comes in, is that you have a stochastic coupling, right, of these gluonic fields to this random distribution of sources. Now, as I mentioned, the separation between sources and fields is arbitrary, right? What is sources, what is fields? And that's where the beauty of RG comes in, because you say, well, this guy shouldn't care what I call sources and what I call fields. It must be independent of the separation. And that tells you that there's an RG with which these distributions evolve as a function of changing scale. As I mentioned, there's an explicit construction of these distribution of sources, the stochastic distribution. It turns out that for very large nuclei, if you can think of it just as a large collection of color sources that the gauge fields couple to, essentially the central limit theorem applies, and you can describe it in terms of the Casimirs of the color charges in the particular gauge group that you're looking at. So if you're looking at SU3, which is the physical world, then you have the quadratic Casimir and the cubic Casimir. And these are what generate what are sometimes called Pomeron configurations, and these generate Autoron configurations. So for those of you who have taken a particle physics course at some time recently or in the distant past, Pomerons and regions were the entire essence of S-matrix theory, okay, before QCD came about. And because it described high-energy scattering beautifully, these effective constructions, but no one knew what these objects were. I mean, they were kind of these mysterious kind of things. And you see that in this construction, they just emerge very simply from the dynamics of these color charges in this EFT kind of construction, high energies. And it turns out that there's a alternate formulation of the EFT entirely in terms of these Pomeron and region objects that's sometimes called Lipato's region field theory, and one can map the two to each other. In essence, in the color glass case, you deal with path order exponentials. So you deal with the group, while in Lipato's theory you deal with the algebra. So those are the log of the path order exponentials in one case or the other. So there's kind of this very nice interpretation. So how do you compute things in this framework? So here you have a theory of sources and fields, they're strongly correlated fields, and you have these sources that they couple to. How do you actually compute? And the problem there is that of strong fields. So you might have heard of the Schwinger mechanism, for example, for pair production, strong electromagnetic fields. And there's an analogous one in QCD, where you think of, so here's a simple example in terms of phi cubed, where now you think about, you have these sources and sinks, and so you say, okay, well, a source can emit a particle or absorb it, and so you call, this object, so the sources can lie on top of the Schwinger-Keldysh contour denoted by plus or on the bottom, and you can construct your Feynman and Whiteman propagators on this contour. And so then you can think about all possible topological cuts between pluses and minuses, stuff that lives on the upper part of the contour and the lower part of the contour. At the end of the day, you just set plus and minus equal to each other when you compute physical observables, so that's a standard Schwinger-Keldysh framework. And so you can use this to just compute systematically, okay, correlation functions in this framework. And so these things are sometimes in region field theory in the old days. They're sometimes called the AGK cutting rules. So it's essentially the combinatorics So if you think about how you compute in quantum field theory, you have all these vacuum-to-vacuum connected graphs, and then you take various cuts of these vacuum-to-vacuum graphs to produce particles, final states, and there's a combinatorics there. So it's essentially the cluster decomposition of 2-point, 3-point, endpoint correlation functions. And you can think of these in terms of the combinatorics of cut and uncut subgraphs, okay, that contribute to a given multiplicity of particles. And so instead of thinking about this in this mysterious language of Pomerans and regions from S-matrix theory, you understand now in this strong field EFT that I constructed of sources and fields in the light cone that it's a very general consequence of unitarity of strong fields. So when you impose unitarity constraints, that really explains these cutting rules very simply in terms of the combinatorics of cut and uncut and cut graphs. Okay? So these objects can be really understood in a modern sense as objects that really enforce strong field unitarity. So, I had the CFT that I wrote down for you, right? And so the natural question is to ask, well, is there a vacuum associated with these strong fields? How do you compute the classical solutions in this case here? So you can ask, okay, what is the classical saddle point of this object here? So what you do is you take the saddle point to this effective action in the presence of these sources, right, which are then have to be averaged over, they're stochastic. And you can ask, what are the classical solutions? And it turns out there's a really beautiful classical solution, non-perturbative solution to these equations. So essentially, you can think about it as, so here you have your shock, and it's like a delta function, and so these are light cone variables I'm working with. So it's a delta function x minus spatially, it's highly localized. On one side of the shock, you have the pure vacuums. So AI and A minus are 0 if you work in a certain gauge. On the other side of the shock, you have another pure gauge. Okay? So the field strengths are 0 on either side of the shock wave. So all the field strengths are highly localized on the sheet here. So this is the transverse plane, so it's a two-dimensional plane here that's going out of the board. And so you have this kind of remarkable solution. You have vacuum one side, vacuum on the other side, but these are two different pure gauges. Okay? So they're discontinuous. So you can think about these as different vacuum. And it turns out that this has a very deep connection to this whole language of asymptotic symmetries that was popularized by Strominger and his collaborators for some time now. And there's a whole subfield of high energy physics on its own. And essentially these asymptotic symmetries in this particular case can be thought of as the breaking of the symmetry of large gauge transformations. So if you have a gauge field here and a gauge field here, so you would in principle have gauge symmetry of large gauge transformations, but because you have this singular object here, they're discontinuous. So you're breaking the global symmetry of large gauge transformations when you cross this. So when you break the symmetry of large gauge transformations, what Strominger taught us is that this is related to a triangle of identities. So essentially, the objects, the goldstones of that object, can be thought of as having vacuum transitions, which leads to something called a memory effect. So in gravity, there's something called the gravitational memory effect, having to do with the asymptotic symmetries of gravity. And similarly, as I'm going to describe, there's a color memory effect in QCD. And this is also related to then soft theorems governing the properties of amplitudes when you take one of the external momenta to 0. Okay. So remember I said that the solution is that of pure gauges on either side of a shock wave. The other feature is that the gauge fields are entirely independent of x plus. Okay, so they're translationally invariant in x plus. Okay, so these defects don't know anything about light cone time, so they're kind of sitting there. So what you can do is you can project that to null infinity, right? And you can do a stereographic projection of this two-dimensional plane to a celestial sphere that's sitting at null infinity. So instead of working with light cone coordinates, So the usual formulation is in terms of retarded time, so that's these u's, okay, the radial distance, and the holomorphic coordinates z and z bar that live on the celestial sphere, okay? And the map between the two is as follows. X plus is proportional to the radial distance. X minus is the sum of this times r times z bar. And the transverse coordinates, x and y, are related to z and r in this fashion here. So now if you scale these objects by lambda, or lambda inverse, and so on, okay, such that the measure is invariant, the metric's invariant. So then if you take the limit lambda going to infinity, that corresponds to r going to 0, infinity, x plus going to infinity, so you're really boosting to null infinity here, and x minus going to 0. So that's the highly Lorentz contracted thinking. So in this picture, when you solve the Yang-Mills equations, you can understand the picture as this color memory effect, as if you took a pair of, as representing the result of taking a pair of quarks, or taking a quark and doing a loop like this, right, as a function of this retarded time, right, at null infinity, and where you have a flux now going through this object here. And what happens is that these quarks, they don't end up where they start with. Okay, so you have a quark and it's going through this thing and ends up at a slightly different position. Okay? And that's the color memory effect. By the way, in gravity, okay, this is what people will be looking for when they put satellites in space as interferometers and look for actual physical displacements of their detectors. Okay, that's a gravitational memory effect. And so there's going to be satellites in space which are about 50 million kilometers from Earth with radii which are over a million kilometers away. So their satellites is a million kilometers distance, and they're going to try and measure this gravitational displacement. And QCD, this precise analog of this, and this was discussed in these papers by Andy Stromage and his students, and then by us with later quantifying this in QCD. And so you can, the effective objects here are these Wilson lines of these color sources, path or exponential of these color sources, which can then be thought of as vertex operators in the celestial sphere. So all the dynamics in this picture is transverse dynamics in the celestial sphere described by correlators of these Wilson lines. So I mentioned the RG, that when you construct an operator, it's independent of what you call sources and fields. What are the defects? What are the gauge fields? Right? The projectile, the probe doesn't know about it. And so that gives you a renormalization group equation where you look at how these operators that you measure vary as a function of rapidity. That's the velocity with which of the boost. So you can think of rapidity as kind of the boost variable, which you're changing in velocity. And this can be expressed in this RG form, where this object here, this is the operator, right? It looks like a Fokker-Planck equation in the space of functional fields. Okay, so this has a form of a Fokker-Planck-like equation where this is like a diffusion. This is a diffusion equation where chi is a diffusion coefficient in this functional space. So what you have is kind of these wee partons on this celestial sphere, sort of they're kind of dancing around, right? And you can compute the correlation functions as you vary time or rapidity, okay, on the sphere. And so that's this denotes here the separation of source and fields, saying that this is dynamical. And so you can compute semi-classically what happens as you change sources to fields, and the requirement that the result be invariant under the separation is what gives rise to this equation here. So what you have is a kind of Langevin diffusion of wee partons in the functional space of color fields, and that can be represented as a hierarchy, so a BBJKY kind of hierarchy of endpoint Wilson line correlators. And it turns out that you can actually solve this numerically. You can solve this Langevin equation on a lattice, and this is what you see. Okay, you start with some initial condition as some initial rapidity, and as you boost, you see that these objects here get smaller and smaller. Okay, and that's the this close packing scale that I was telling you emerging, where you see that you get very close packing of these gluons as you go to these very high glues. So that's a result of an explicit solution of this RG hierarchy of equations. Okay? So as I mentioned, let's consider a specific case. So to be very particular, so again, I'm in the target, boosted target frame, where you think of this projectile as interacting with a boosted target, so it's a shock wave. Now here you have a quark in position X, anti-quark in position Y. Okay, and the operator then are these vertex operators. These are these V of X, V dagger Y. And what you can think of it as, you have a quark that comes and hits a shock wave, gets color rotated, okay? And then this other guy gets color rotated in the opposite way. Okay? And this object is proportional to the cross section, the S matrix for the scattering. So this is actually precisely the S matrix for the scattering in the shock wave background. Now you ask yourself, okay, what happens now if I boost the projectile a little bit and I emit a gluon in the process? So then a gluon also then scatters to the shock wave. So this difference between this cross-section and this cross-section, the boost, is what then can be thought of in this specific instance as giving you the RG. Okay? And so this is the dipole operator. So it's a trace of the product of Wilson lines at two different spatial positions. And the expectation value in the shock wave background is a function of rapidity. And that's related to a kernel, which is this BFKL Hamiltonian I mentioned at the start of my talk. And that was something you got from, remember, 2 to n amplitudes. And this is entirely in the language of defects and bulk fields and Wilson lines. And so this object here on the left-hand side is proportional to the very same object on the right. Okay, so that's the likelihood that the projectile does not scatter. The S matrix doesn't change. But then here's the scattering of the gluon, right? That's the additional spatial variable of the gluon. And so you can write this as the expectation value of the product of the traces of these operators. But it turns out that in a mean field approximation for a very large number of sources, the large NC limit, you can write this expectation value of the product as a product of expectation values. And that gives you a closed form expression in terms of entirely this object here. So if you think about this as some kappa, right? So this d kappa by dy is kappa minus kappa squared. Although a more complicated kind of equation there. And you can solve this equation, okay? There's no known analytic solution, but there's a very good approximate solution, as well as numerical solutions. Now, if you take then the low density limits, if you expand out these vertex operators to lowest order in these sources, the defects, and you plug that back in, that gives you the BFKL equation. Okay? So we recovered a result that we obtained in terms of amplitudes, right, 2 to n amplitudes, entirely in this kind of language of impurities living on a sheet and the bulk fields that surround it. But this equation is very rich, and this gives you all this kind of very complicated multi-Pomeron type diagrams, which then, in this low density limit, they reduce to this BFKL ladder that I started out with. And the solution is remarkable. It has, this equation has a UV fixed point, which is BFKL, but then it has a non-trivial IR fixed point. And that IR fixed point corresponds to the S matrix going to 0. So that's the molasses scattering that I was talking about, that the projectile scatters over is very dense. And that's a result of this picture that I mentioned. And so if you solve this in momentum space, if you study this in momentum space, this wave function of this object, of this projectile, as a function of transverse momentum, has this really beautiful kind of solitonic type structure. And that moves with increasing rapidity. You can think of it as time as moving to the right. Okay? So this tells you that the scales are getting harder and harder, making this approximation better and better, weak coupling framework. But it's also highly non-perturbative because it has this non-trivial fixed point, of this very strongly correlated gluon fields at the scale here that increases with boost. Okay. And as parenthetically, I should mention this decay framework, this describes this equation here, this nonlinear equation, can be mapped to the Fisher-Kolmogorov-Petrovsky-Piskunov equation for pull traveling wavefronts in statistical mechanics. And actually, there's been a rich dialogue between StatMech and high-energy QCD over the last 2 decades as a result. You can now go into precision. There's a huge amount of work. There's decades of it. The state of the art is next to leading log in this framework. Specifically in SUSY, which has been performed. There's all kinds of computations of various physical processes, and it's a very active, thriving field. You can actually make comparisons to data, predictions for future experiments, and so on. So it's a very thriving field. That's there. So in my last 8 minutes, 5 minutes, yeah. Let me just expand on some of the things I said. So I mentioned that you have this picture of these static sources on the light cone that are coupled to these dynamical gauge fields in the bulk, and there's this beautiful RG that emerges. And so, but we know that at some point, this picture of static sources must break down. Because, so if you think about, these, again, if you think in terms of a glass, right? So this window pane. So why is a window pane solid rather than liquid? It's because it has these impurities, right? Which kind of prevent it, right? And there's kind of stochastic, random impurities. And they prevent it from actually flowing into a glass, right? And that time scale is much larger than sort of natural time scale, right? It's millions of years. And these impurities corresponding to these highly energetic partons on the light cone have a similar feature, which is if you just say that, okay, I have the shockwave field that's described in terms of these sources, color sources. If I just naively estimate what the lifetime of these are as you boost, this is the boost momentum, to higher and higher energies, it will tell you that the lifetime of this configuration, this lumpy semi-classical configuration, would be much longer than natural time scales. The problem. Natural time scales is confinement time scale, lambda QCD. Okay. And that's the glass in the color glass. Okay. However, we know since Coleman that there are no stable classical glue balls or shock waves, okay, in gauge theories. Okay. These things must decay and radiate. So how do we kind of understand the decay of these impurities in this framework? So how do these impurities that sit on the sheet actually decay? Okay. And so that actually goes into some very interesting, beautiful stuff, is that what happens when you, so what's happening? So you have this high energy scattering, and you're producing all these overpopulated glue, and at some point, perturbation theory breaks down, and you can think of actually kind of spontaneously breaking 2 global symmetries in the process. One is you break the symmetry of large gauge transformations that I mentioned, but you also break Poincare invariance, right? Because you have a specific frame that defines the shock, okay? And so you can, if you ask now, what are the microstates that define the shock? So what is this regized object that's actually scattering off this probe, right? You can think of it as a collection of microstates or Goldstone modes, right, of these broken symmetries. And specifically in the case of the broken large gauge transformations, that corresponds to the U1 cross U1 group of the diagonal generators of SU3, in the SU3 case. Okay? And that's the group of large gauge transformations. So in some sense, in that picture, you have a kind of abelian kind of rotation where you can think about these really in terms of creation relation operators in that rotated frame. And so then however, these are pseudo-Goldstone bosons precisely because you have fixed occupancy n, which is of order 1 over alpha s. Okay? So n is not infinity. So essentially these microstates are separated when you diagonalize that. they're separated by slightly different energy levels, which are this characteristic close packing scale I introduced, right, that comes out of the RG equations, divided by the occupancy. So now imagine I have, instead of this static configuration, I really think of it as a collection of microstates, okay, which have slightly different energy spacings. Now, in the limit that n goes to infinity, they become all degenerate, and then you have a pure classical field, right? But in the real world, we have finite occupancy, so there's a large n, 1 over n type correction that occurs. So now imagine you are emitting a very soft gluon, right? And that tickles this shock wave, okay? But it tickles it, so if it were a harder gluon, it wouldn't resolve this microstate structure. It can't resolve the slightly different transverse momenta characterizing the shock wave. However, if it's sufficiently soft, as given by the scale here, then the shock wave can emit one of these energy levels here, can be excited, and can emit, there's an escape velocity, so to speak, for these guys, for this self-bound state to kind of decay. And that is just given by the characteristic decay time scale, which is 1 over this. So on this time scale, the color glass will become a color liquid. And so now if you're looking at doing perturbation theory, and you're just focused on very hard transverse momenta at some order in perturbation theory, it's fine. However, when you go to high orders in perturbation theory, such kind of contributions will affect the phase space in your integrals that you do when you compute to high orders, the Feynman diagrams. Okay? And that's going to change your power counting. What you thought of as a log is now a pure power, okay, or vice versa. Okay? And so this will lead to what's sometimes called a breakdown of rigidization. So one of the fathers of this BF-Gale framework has come to similar conclusions from very different perspectives than I have. So this is work I did with Gyatwali some time ago and is in preparation with P.P. Nair. And so this will actually modify the phase space for gluon emission. So what it's telling you is that to understand precision QCD, to really compute to high orders, right, in the radial limit of QCD, you have to take all these considerations into account carefully, which is not something you normally think about, right? It's not, you think, well, it's some kind of leading order kind of picture that I have, and then, you know, at high orders, I do whatever. Here it's telling you that at leading orders, things kind of look okay, but then when you go to high orders, you have to really think carefully about, you know, Goldstone dynamics of these V-parton modes at high energies. So in my last 1 minute or so, I want to say that this has a very rich physics. So some of you may know that there's a new form of matter, the quark-gluon plasma, that was discovered at RIC and at the LHC. And you can actually follow all of this logic, impurities on the sheet and gauge fields in the bulk, and follow that all the way, right, in collision to the formation of, and there's very rich physics of turbulence and hydrodynamic attractors involved. If you're interested, look at my review on this. And what's remarkable is there's only one scale in the problem, right, in the weak coupling regime, and that's the scale here. You can compute what the temperature is in terms of the scale, and you can compute what the time it takes to thermalize this as well. And you see that when you go to very large scales in the radial limit, as you boost to very, very high energies, the coupling goes to 0, such that times the occupancy is fixed, you get very rapid thermalization of such a system. So thank you very much.
It's time for 1 or 2 quick questions. So, yes, please.
So, at the end you mentioned the breaking up of the concurrent invariance by this glass condensate and the Goldstone model. So if I take n to infinity, so things are stable, is there a way to describe the processes you were describing before via interaction of the bulk field with some effective theory of Goldstone bosons on this defect? The mechanism looks pretty different in
Yeah, I think so. So I think the shock wave actually becomes stable in that regime here, right? So it really is then like a string,
Yeah.
Right? So then you're really talking about excitations on the string, that live on the string. And so that's that limit, indeed. And so then, but you still have this, you still have taken account of both the gallstones or the broken symmetries, right? But they're true gallstones in that case.
Because for the timeline case, we know how this effective theory looks like. And so is there a boosted version, and can you add interaction to the bulk? Is this been done?
Well, yeah, so that's what actually I'm describing, essentially.
Yeah.
So I'm working at fixed n, right? So, yeah, so is what you're asking that you take n equal to infinity limit, so to speak?
Yes.
Right? It's not clear that's a smooth limit in this case here, because this intimately depends on the product, the coupling, and the occupancy is being order 1, right? So if you take that, if you keep that fixed, right, then taking n to infinity is literally like putting alpha to 0, and then you get a non-interacting theory. So it doesn't commute with a non-interacting theory, which is that extreme in this limit. So these are discontinuous limits.
Okay, I think we are already over time. Let's quickly move to the next speaker. And thanks.